Hi, I'm Jonathan Aldrich. Today let's talk about scoping rules. First of all, let's talk about the concept of declarations and definitions. Declarations introduce a name, and if we're in a typed language, they also give its type. For example, in C, a declaration might read int x. A definition, on the other hand, fully defines an entity. We specify the value for variables in definitions, and for functions, we'll specify the function body. For example, int x equals 0 would be a definition in C. Some common rules that you see in programming languages include declaring variables and functions before using them, and defining them before using them. What is the rationale for these rules? Well, declaration before use makes it possible to write a one-pass compiler. So when you call a function, you know its signature, and so you know how to call it, how many arguments to pass. You can type check it. In general, for example, in C, this requires separating declarations from definitions, because you could have two functions that call each other, and so one of them has to be first, and then if you only had definitions, then you would have to declare one of the functions after using it. But if we declare them both first, if we declare the one that is defined second before we define the first function, then we can have declarations for both functions in scope whenever they are called. For things like variables, a common rule is definition before use. This allows us to avoid accessing a variable that's not defined. Some languages will relax these for classes, fields, and methods. Java, for example, initializes fields and classes lazily. And for methods, it's no big deal because they're compiled ahead of time. But local variables still have to be defined before they're used, because otherwise we don't know the value of those variables. Let's consider static scoping. Here we have an example of code with an outer class in Java, an inner class nested inside the outer class, and then a function. And both the outer class, the inner class, and the function define the same variable x, except it's not actually the same variable. So let's think about if we have a print statement in the function, but not within the if statement where the variable x was declared. Which x is it going to print? Will it print 1, 2, or 3? Think about that for a moment, pausing the video if you need to. So the answer in Java is that the most recent binding of x in an enclosing scope is the one that's printed. So in this case, the x from inner will be printed, and this will print the number 2. That's, in fact, the rule that's used by most programming languages. So with static or lexical scoping rules, a scope is defined in terms of the lexical structure of the program. Compilers can determine what is the scope of entities such as variables and functions. Bindings for identifiers can be resolved by examining the code and looking for the enclosing scope. Typically, we look for the most recent binding in an enclosing scope. So the most narrowly enclosing scope for the place where we're using the variable. Most compiled languages, such as C and Pascal, employ static scoping rules. The history of this comes from the most closely nested rule from Algol 60. In this rule, an identifier is known in the scope where it is declared, and in each enclosed scope, unless it is redeclared in that enclosed scope. So this turns into a rule the compilers can use to find the variable that is being used at a given point. So to resolve a reference to an identifier, we examine the local scope, and then statically enclosing scopes one by one until a binding is found. How is that actually implemented? Well, we have to consider how do we access variables from outer scopes at runtime. What we do is we access non-local variables via chains of static links. So if we're in variable C, and we access a local variable in C, we have it in the local frame of that function. And the frame pointer tells us where to find it. But if we're in C and we want to access a variable in B, where C is nested in B, or in A, which surrounds both C and B, then we can use static links to go from our scope in C to the scope of the surrounding functions. So this is graphically shown on the right, where C has a static link down to B. The function D might have a static link down to B as well, because both C and D are nested in B. And then E might have a static link to A as well as B. So each frame here points to the frame of the routine inside which it was declared. In the presence of recursion, there could be more than one frame for the surrounding routine. So we'll simplify things for a moment. In the absence of passing functions as parameters, the correct instance of the routine that we're nested inside is always the one that's closest to the top of the stack. And we'll look at cases for passing functions as parameters later. So you can access a variable in a scope that's k levels out simply by following k static links and then using the known offset within the frame that you find. Let's look at an example of this. Here we have a program A that has subroutines B and D within it. And then B also has subroutines C and D within it. This is Pascal code, by the way. So again, we're going to declare the variable x multiple times. And if we look in procedure C, we can think about which version of x is being printed, which instance of the x variable is going to be printed. So think about this for a while. You can stop the video if you like. On the right, I've shown the static links as well as the return links from one procedure to another. So in static chains, what we're going to do is we're going to use the static link from the frame for C to get the frame for B. Then we'll use the static link from the frame for B to get to the frame for A, and there we find the variable x whose value is 1. So the program will print 1. There's another kind of scoping called dynamic scoping, which is an alternative to static scope. It's not used very much anymore. It was initially used because it was simple and because we didn't know any better. But it turns out to be the wrong thing most of the time. In dynamic scope, you don't have static links. You just look up the latest binding of a variable in the stack using links from one frame to the next. So this would be the next frame pointer. Each frame has a next frame pointer that refers to it. So we can just go down one frame at a time in the stack using these calling frame pointers. Unfortunately, when we find a variable, it might be a variable from completely unrelated code. And this can make reasoning based on the program text hard. Let's look at an example of dynamic scope. Again, this is the same program I showed you before. We have some nested procedures, and we have multiple declarations of different variables that are all called x. With dynamic scope in procedure C, which x will be printed? Again, take a moment to look at it and think about, instead of following the static link, just going from a frame to its calling frame, using the links that go just from one frame to the next. Okay, so in dynamic scope, we're going to start with a frame for C, and we're going to look at what's the next frame in the stack. Who called C? Well, in this case, the procedure D called C. And so the calling frame from C is D. We follow that link instead of the static link, and we see, oh, here's an x, the value is 3, and so we'll print 3. So Common Lisp implements dynamic scoping, and it would print 3 by default here. Let's do a little in-class exercise using these principles. Given this slightly simpler program than the one I showed you, what is printed under static scoping and dynamic scoping? Pause the video, think about it, and then we'll check your answers.